Hello everyone, welcome to our differential equation class. In this video we are going to review for our midterm exam 2. Let's recall the exam settings. First, the exam covers all we have seen in chapter 1, 2 and 4 with emphasis on 2 and 4. The exam is 2 hours. This Thursday opens at 1 p.m., is due at 8 p.m. and closes at 10 p.m. So the exam is open from 1 p.m. until 10 p.m. During that window you can start the exam at any time. Why the exam is due at 8 p.m.? Because if you start at 8 p.m. or before, you have the 2 hours of the exams in the window where the exam is open. So if there is any problem with the internet connection, you can log back into the exam. If you start after it's due, then you still have the 2 hours to do the exam. So that's not a problem. The problem is if you have an internet problem after it closes, then you cannot log back in. So your exam ends here. So you are risking losing exam time if you have an internet connection problem when you start after 8 p.m. Okay, the exam is online in D2L. We use the Lockdown browser, the webcam. The exam has 10 problems like the exam 1, 7 multiple choice problem, 3 written response, approximately 60% of the grade for the written response and 40%, 42% for the multiple choice. You have a formula sheet included in the exam. The calculators allowed are the ones that we list in our D2L site. No phones, no notes, no review sheets. The practice exam, here it should say practice exam 2, is online, so you can take it, and there is extra credit for the multiple choice part. And there are practice problems also online in our D2L site. So these are the settings of our exam. And in this review, what we do is we solve problems that they have a similar difficulty than our exam problems. These are review problems from chapter 1. So we are not gonna solve them. I'm gonna post the solutions to these problems, but you have the solution to practice. Then here we have problems from chapter 2. Again, we are not going to go over those problems because, well, we don't have time in 50 minutes to go over all these problems. But this is chapter 2. We are going to post the solutions to these problems. And we are going to focus on chapter 4, which are these problems here. So we are going to start solving this problem from the bottom up. So problems 12 to 9. Alright, so that's the plan for the video today. Okay, let's start with our last problem and work our way up. So we have a second order linear differential equation with constant coefficients. That is the left hand side equal cosine times a Dirac delta. So this describes an impulsive force with some non-zero initial conditions. Let's see how we can solve this problem. So the solution is, let's compute Laplace transforms on both sides of the equation. Laplace transform on the left side is going to be something like this. And on the right side, well, Laplace transform of the whole right hand side. Cosine of t delta t minus pi. What do we do on the right hand side? Well, we have a result that says that the Laplace transform of any function, continuous function, times a Dirac delta at t minus some constant c, this is going to be the function evaluated at where the delta is singular at c times an exponential negative cs, but this is only in the case that c is 0 or positive. Otherwise, this is 0 for c negative. So what is our c here? Well, the c in our case is pi. So we need to use this result with c equal pi, which is positive. So we are going to use this result here. On the left side, we use linearity. So now that we are at it, we say this is equal to the Laplace transform of y double prime plus the Laplace transform of y prime minus 6 Laplace transform of y. But on the other side, this is the function, the cosine, that is evaluated where the delta is singular. So at pi, and then we have the exponential negative pi s. Alright, what do we do on the left side? On the left side, we change derivatives into multiplications, and we are going to have that this is equal the Laplace transform of s squared. So s squared Laplace transform of y minus, now we have s multiplied by y at 0 minus the derivative at 0. This is the first term. Then we have plus s Laplace transform of y minus y at 0, and then minus 6 Laplace transform of y. And on the right side, well, let's recall that cosine of pi is well known, is -1, so we end up with just negative exponential minus pi s. Alright, what are our initial conditions? Our initial conditions are these two, so that means that here we have equal 1. Over here we have that this quantity is equal to, and this quantity here is also equal 1. So we can pull common factor the Laplace transform of y, and then we're going to have the characteristic polynomial s squared plus s minus 6, all multiplying the Laplace transform of y. Then we have minus s minus 2. These are these two quantities here, and then we have minus 1. And all that has to be equal minus exponential of negative pi s. So when we move everything to the other side, now we can move these terms to the other side. Of course, what we have here is minus 3. So it's going to be plus 3 on the other side, and then we divide everything by the polynomial here. So in one line we can solve for y. And this is going to be negative exponential minus pi s over, so plus s plus 3, and then both terms I'm going to divide it by the same denominator. And the denominator in both terms is going to be s squared plus s plus 6. Oh, sorry, minus 6. Careful with the signs. And the same denominator over here. S squared plus s minus 6. And that is the Laplace transform of the solution we are looking for. So now what we need to do is find the function such that this is the Laplace transform. Okay, how we proceed now? Well, that depends on what we have in the denominator. So we need to compute the zeros of the denominator and see what we get. Whether they are real or complex, we do different things. Okay, so zeros of the denominator, we need to find the solution of s squared plus s minus 6 equals 0, which is s plus minus is going to be equal 1/2 then we have a negative 1, a plus or minus square root of the coefficient that of the linear term 1 square minus and 4 times 6, but it's minus 6. So something like this, and this is 1/2 minus 1 plus minus the square root of 1 plus 24. So we see this is 25, the square root is 5. So we end up with s plus minus being equal 1/2 minus 1 plus minus 5. So we are going to get two roots, s plus, which is 4 divided by 2 is 2, and s minus, which is negative 6 divided by 2 is negative 3. So two different real roots. Alright, so that means that s squared plus s minus 6 actually can be written as s minus 2 multiplied by s plus 3. And we can verify that this is the case because we have our s squared, then we have negative 2s plus 3 is plus 1, and then the negative 6. Perfect. So it's always a good idea to double check what we do. And now that we know that, then the Laplace transform of y, it has a simpler expression. It's going to be exponential minus pi s. Then we're going to have a negative 1, I'm going to put it here, and then I'm going to say this is actually equal s minus 2 times s plus 3. And then recall we have the other term that is s plus 3, and down here we have the same, s minus 2, s plus 3. And here we got lucky, and the denominator cancels with the numerator. We can call it lucky, or we can call it we chose the problem carefully. Anyways, there is a simplification there. So the second term is done, because we know that 1 over s minus 2 is actually the Laplace transform of exponential 2t. So that term is done. So we need to work here only. And what we're going to do is we're going to do partial fractions only here. We never include in the partial fractions any function that is not a rational function. So exponential is not included. So now we go to partial fractions only for this part. Partial fractions. What is that? This is nothing more than rewrite this rational function as a sum of simpler rational functions. Notice that we are including the negative 1 here. The constant goes there. What is not there is the exponential. Alright, so what we have is that negative 1 over s minus 2 s plus 3 is an addition of simpler rational functions, and when the denominator has this form, we know that the rational functions are going to be a constant over the first factor plus a constant over the second factor. So how do we find the constants? Well, in the usual way, we redo the sum. So we go back to s minus 2 times s plus 3, and the numerator we are going to have, of course, a multiplied by the other factor, s plus 3, and here b times s minus 2. And at this point, the denominators of the last and the first equation are the same, so the numerators have to be the same, and the numerators are that negative 1 is equal a s plus 3 plus b s minus 2. And this is an equation that has to be true for all s. So we can choose. Actually, one can prove that this equation always have solutions for a and b. Once you know that, you can just evaluate at different values of s to find the solutions. For example, we can evaluate at s equal which s we are going to choose. Well, we choose the s such that this factor vanish. These are the simplest one. So for example, s equal -3. Then -1 is equal 0 plus b times -3, -2. So from here we get -5, and then b is nothing more than minus, we have negative, so let's say that this here is -5, and this negative sign is going to cancel that negative sign, and we are going to get a positive 1/5. So that's the first constant. The other constant is when we evaluate, we compute the other constant when we evaluate at the other root, so at s equal 2. So we are going to have -1, which is equal a 2 plus 3 plus 0. Then we have 5, and the negative sign stays in this case, and we have -1/5. And these are our constants. Okay, so let's go back here and let's write down what we obtain. What we have is that the Laplace transform of the function we are looking for is actually an exponential negative by s, and then we are going to have -1/2, 1/5, 1/, we need to be careful where we place this constant. This constant goes with that function. So let's write it down. -1/5 goes with s minus 2, all multiplied by the exponential, and then positive 1/5 goes with 1/s plus 3. And then recall we had the lonely factor, or the lonely term 1/s minus 2, that we know what to do there. We know that. So that's it. And now we use this is the same equation here, and we have a similar equation over there. So what we are going to use now is that we know what is the Laplace transform of exponential at for any a. This is 1/s minus a. So we use it for a equal 2 as we did before, and also for a equal -3. And then we have that the Laplace transform of y is the exponential. We haven't done anything with exponential yet. The factor 1/5, we can take it outside. And then we are going to have the Laplace transform of exponential 2t, that's a t here, with a negative sign, and then plus the Laplace transform of exponential -3t. And recall we had here already the Laplace transform of the exponential 2t. So what do we do now with this exponential there? With this exponential. Well, now we need to recall so first of all, what we're going to do is we are going to distribute that, and then we are going to see that, or remember that whenever we have an exponential negative cs, now recall c is pi in this case, the Laplace transform of something we know, like it happened here and here, we know that this is the Laplace transform of the step t minus c and the function shifted. So we are going to use this formula for, okay, c is going to be equal pi, of course. F is going to be equal exponential 2t, and f is also going to be exponential negative 3t. We are going to use this formula twice. And then we get that the Laplace transform of y is going to be the 1/5. Now these two factors together are going to create a negative Laplace transform of u t minus pi exponential 2 t minus pi. Then these two factors together, are gonna create, the 1/5 is already outside, the Laplace transform of u t minus pi exponential negative 3 t minus pi. And we have still the factor Laplace transform of exponential 2t. And the 1/5 only multiplies the first two terms. That's it. We got our result. From here we conclude that our function is gonna be the 1/5. Then we are gonna have a step t minus pi common factor from the exponential negative 3 t minus pi minus the exponential minus, this is ugly, the exponential of 2 t minus pi, and we need to add the exponential 2t. And this is how we use an impulsive force on the right hand side, and we solve an equation with an impulsive force using the Laplace transform method. In our next problem, we still have a second order linear differential equation, but our right hand side is a discontinuous function, is a step. To simplify the problem, we have 0 initial conditions. So this problem is again solved using Laplace transforms because of the right hand side. Let's compute the Laplace transform of the whole thing. Laplace transform of the second derivative plus 4y prime plus 4y, and here has to be equal the Laplace transform of the step, which we know what that is. The Laplace transform of the step is according to the in Laplace transform table, so we can put it here. Yeah, let's put it right here. Laplace transform table says this is going to be exponential negative 3s over s. Okay, what do we do on the other side? Let's move it a little bit lower here. What do we do on the other side? On the other side, well, this is equal the Laplace transform linearity. The linearity property of the Laplace transform says that this is 4 Laplace transform of the first derivative plus 4 again the Laplace transform of the function. And now, since we don't have any non-zero initial conditions, so the initial conditions are both 0, this is just the same as s squared Laplace transform of y plus 4s Laplace transform of y plus 4 Laplace transform of y. And recall this is equal exponential negative 3s over s. So we can pull common factor the Laplace transform of y from these three terms, and we get something simple, that is s squared plus 4s plus 4 all multiplies the Laplace transform of y, and this has to be equal to the exponential negative 3s over s. So we obtain what is the Laplace transform of y. This is the easy part of the calculation. We have an exponential negative 3s, and then we have 1 over s, and then s squared plus 4s plus 4. Alright, as we did in the previous problem, whatever we do now depends on what are the zeros here. So let's find out what are the zeros of the characteristic polynomial. S squared plus 4s plus 4 equals 0. That means that s plus minus is going to be 1/2, then negative 4 plus minus the square root of 4 squared minus 4 times 4. That's the formula, and what do we see? We get that this is negative 2. So we have a repeat root negative 2. So this implies that s plus is equal s minus is equal negative 2. So our denominator, s squared plus 4s plus 4, is actually s plus 2 squared. Well, that makes things not so complicated. We have an exponential negative 3s, and then we have 1 over s, and then s plus 2 squared. This is the function we are dealing with. And now we need to, now that we know that this is the denominator, we can do partial fractions. And we know what partial fractions to use because of that denominator. So let's go to partial fractions. What happens when we have a denominator like that? A product of two polynomials, one is a perfect square, the other is just multiplication by s. Well, first of all, we are going to do partial fractions only with the rational function. The exponential is never in the partial fraction decomposition. We only do it here. And well, there are two possibilities. Both are correct. You choose whatever you like better. There are two possibilities. One is to write s over s plus 2 squared as a constant over s plus a constant over s plus 2 only plus another constant over s plus 2 squared. That's one possible partial fraction decomposition. The other is equivalent in the sense that there is a relation between a, b, and c and the new constants, and is this. We say this is an a tilde over s. A tilde is going to be equal s, but then we have here b tilde s plus c tilde. These are going to be different constants over s plus 2 squared. Either of these two decompositions are correct. There is, actually, we can remove that. There is a way to relate the constants b and c with b tilde and c tilde. So this is the same decomposition. They are equivalent. So, well, we have to choose one. We're going to choose the first one for no reason. Okay, we choose the first one. So let's copy the decomposition here. Copy, paste. Let's work with this decomposition. And what we do here is, of course, we rewrite this addition as one single fraction. There it is. S plus 2 squared. And then here we are going to have a multiplied by s plus 2 square plus b multiplied by s plus 2 plus c multiplied by s. So that is the addition. Verify that this is correct. Then we simplify the denominators, and we have our equation that we need to satisfy for all values of s, and this is a s plus 2 square plus b s plus 2 plus c s, and this has to be true for all s. Okay, so one can prove that this equation for all s has one solution. A, b, and c can be proven. We are going to use that, we know that fact, and we are going to just evaluate this equation at different values of s and get the constants. For example, we have two roots, so these are the first two values of s we are going to choose, 0 and negative 2. So let's start with s equals 0. So we have 1 is going to be equal a 2 square plus 0 plus 0. So from here we get a. A is just 1/4. Okay, we got a. Then these are the easy choices. S equal negative 2. So we have 1 is going to be equal 0 plus 0 plus negative 2 c. So from here we get c. C is going to be negative 1/2. Again, these are the easy choices. And now what do we do? Well, now we evaluate at any other s that we like, because we ran out of roots. So let's say 1. So we are going to have 1 equal a. So we have 1 plus 2 all square. Then we have b multiplied by 1 plus 1 plus 2 plus c multiplied by 1. So the equation is 1 is equal 3 squared, so it's 9a, plus we have 3b and we have c. But we have the values of a and c. We have those, so this is 1 is equal 9/4. Let's put c. C is negative 1/2, which is 2/4, plus 3b. So here we get that, from here we get that 3b is nothing more. We have 1 on the other side, which is actually 4/4, plus 2/4 minus 9/4. All that is 6 minus 9 is negative 3/4. So b has to be negative 1/4. So that's how we obtain all three constants. So now we go back to our Laplace transform of the solution we are looking for, Laplace transform of y, and we say, well, that expression is now this expression with the constant we know. So we still have the exponential negative 3s, and then a is 1/4. A multiplied 1 over s. Then we have plus b, but b is minus 1 over 4, and b multiply s plus 2. And then we have c, which is negative 1/2, and this multiplied 1 over s plus 2 square. All right, and what do we have now? Well, let's distribute the factors, and we are going to have an addition of 1/4, sorry, exponential negative 3s over s. Well, we know the Laplace transform of that. We go to that in a minute. Then we have exponential negative 3s 1 over s plus 2, and then we have minus 1/2 exponential. We need a little bit more space, so it's not so cramped up. Here we have exponential negative 3s and 1 over s plus 2 square. And what we are going to need is, from the Laplace transform table, we are going to need what is the Laplace transform of the step. Well, this is, we already used this expression before, minus cs over s. We are going to use that with s equal 3 here. What do we do here? Well, we know what that is. The Laplace transform of exponential minus 2t. This is, or minus a t. Sorry, this is not for s. What I'm saying here, this is for c. Now, for a, so this is 1 over s minus a, and we are going to use it with a equal our root, negative 2. So we are going to have that. Sorry, that. What do we do with that, with this square? Well, this is also in the Laplace transform table. We have to be just careful, but in the Laplace transform table we have t to the power n exponential at, and the Laplace transform of that is n factorial over s minus a to the power n plus 1. So we use that formula with n equal 1, so we are going to have a factor t, and with a equal negative 2. With all that, our Laplace transform of y is nothing more than 1 over 4 the Laplace transform of the step u t minus 3, then minus 1/4. We still have this exponential here, minus 3s, but now here we have the Laplace transform of exponential 2t, actually minus 2t, and then minus 1/2. We still have the exponential negative 3s, and now here we have the Laplace transform n is equal 1, so t exponential negative 2t. Okay, let's move this equation a little bit to the left so we have space. And now what do we do here with these exponentials? Well, we use again the translation identity that says that whenever we have an exponential, whenever we have an exponential minus cs Laplace transform of some function that you know, this is going to be the Laplace transform of the step shifted by c and the function shifted by c. And we use that formula with f equal exponential negative 2t, and we use it again with f equal t exponential negative 2t. We use it twice because we have two terms, and then we end up with Laplace transform of y is 1/2, again 1/2, 1/4 the Laplace transform of the step. Then we have minus 1/4, and now we use that formula, and then we are going to have the Laplace transform of the step t minus 3, and now the exponential is negative 2 multiplied by t minus 3, and then we have minus 1/2 the Laplace transform of the same step, and now we have t minus 3 because we need to shift the t, and we need to shift the exponential negative 2 t minus 3. So we put all this together and we got our result. The function y of t that we are after is gonna have, let's put common factor 1/4. Why not? And then the step is common factor. Then we are gonna have 1 minus exponential negative 2 t minus 3. And then we are gonna have negative 2, because I pull common factor 1/4, t minus 3 exponential negative 2 t minus 3. And that is how we use Laplace transform to solve a problem, a second order differential equation that has a step function on the right hand side. In our next problem, we need to find a function f such that the Laplace transform of this function is given by this expression, and as usual we need to start finding the zeros of the denominator so we know what type of decomposition we use, what type of partial fraction decomposition. So we start with s squared plus 4s plus 13 equals 0, which means that s plus minus is going to be equal 1/2 always. Then we have negative this coefficient, then plus minus that coefficient square, which is 4 squared minus 4 times 13. Well, we see here that 4 times 13 is bigger than 4 times 4, so the solutions, the roots are going to be complex. We don't need to find what the roots are. Complex. It's enough that we know that they are complex valued. So then we are not going to write this polynomial as a product of two factors, because the factors are going to involve complex numbers. So instead, we complete the square. And what is that? Well, we have our polynomial s squared plus 4s plus 13, and the idea is that we want to write it in the form, let's put it here in a different color. We want to write it as s minus something square plus something else square. That is what we want to do. And to do that, we keep the factor s squared. Then we have to multiply by 2, and because we are multiplying by 2, we need to divide by 2 the same factor, divide by 2, and then we keep the s here, so the second term has not changed, but now we have this 2 here, that what we are going to do is we are going to add its square, and then we are going to subtract that square. So 0, nothing changed. And then we still have the 13. So you see, we add 0 and we multiply by 1. So this polynomial is this polynomial. And now we put this first term together, and there it is. You see, what we have between parentheses is nothing more than a perfect square. This is s plus this number all square. Why? Because if you and then of course we have the minus 4 plus 13, the other two terms. Why? Because suppose you expand, you get s squared plus 2 times s plus 2 squared. Well, that's what it is. So now that we have that, we can rewrite this as s plus 2 squared plus 9, and that is 3 squared. Okay, So our Laplace transform, the function we are looking for, the Laplace transform of the function we are looking for is equal to s minus 2 over s plus 2 all square plus 9, which is actually 3 square. And now we look at the denominator, and this is denominator, we know it from our Laplace transform table. Both the Laplace transform table of sines and cosines multiplied by exponentials actually have that form, because now if we go to the Laplace transform table, let's say here, the Laplace transform of exponential at cosine of bt is very similar to that, is s minus a, and down here we have s minus a squared plus b squared. And notice that denominator, they look pretty much the same if we choose b equal 3 and a equal negative 2. Unfortunately, the numerator is not the same, because when a is negative 2, here we should have s plus 2, and we don't have it. So, well, we can actually shift the numerator with a 0 to actually do have it. So what we can do is we need a plus 2, isn't it? So plus 2 minus 2. And then we have our original negative 2. So we do this rewriting. And here plus 3 square. And now we put these two terms together and the rest. And what do we get? We get a negative 4 from here, obviously. So we can split this rational function into s plus 2 over s plus 2 square plus 3 squared, and notice this is exactly this expression here for these values, but we have to pay a price, and the price is that we have a negative 4 and here 1 over s plus 2 squared plus 3 squared. And now we recall that, oh, we also have the Laplace transform of the exponential at sine of bt. And this is very similar. It's just b over the same denominator, s minus a squared plus b squared. And here we have this denominator is this denominator, because recall we have b equal 3, a equal negative 2, but we are missing the b here. So what do? Well, we put the b, multiply, so b, what is b? B is 3. So we multiply by 3 and we divide by 3. And now here is that factor is in the Laplace transform table, this is in the Laplace transform table, and we are almost done. This is the Laplace transform of exponential negative 2t cosine of 3t, and then we have minus 4/3, and the Laplace transform of the exponential negative 2t sine of 3t. So we put everything together and we got our function f of t. Our function f of t is just the exponential that we can pull it common factor, exponential negative 2t, common factor of the cosine of 3t, and then this factor here that is 4/3, and then the sine of 3t. And this is how we can use partial fraction when we complete the square. Well, not partial fractions now. We completed the square, and properties of the Laplace transform needed to solve this problem. Okay, since we are already at 50 minutes, then I'm gonna post the solutions of all the other problems, and that's it for today. Hope this review is useful, and see you guys in the next video.